I welcome you all into today's presentation. We have discussed the design procedure of various IC engine components in previous presentations. The components such as cylinder, piston, connecting rod, and crankshaft. For better understanding, in today's presentation, we intend to solve some numericals on design of cylinder and piston of an IC engine. It is expected that when we'll solve these numericals, we'll understand the design procedure in a better way. So let's start. First of all, let us quickly recall what we have learned while we designed a cylinder for an IC engine. This is the sketch of cylinder of an IC engine along with piston and connecting rod. When we discussed the design portion, we found the dimensions such as bore of cylinder, length of cylinder, thickness of cylinder wall, thickness of cylinder head, number and diameter of cylinder head studs, and pitch circle diameter of studs. We have found the relevant formulas for all these dimensions. I request you all to please go through the presentation prior to you solve numericals in this presentation. So let's start solving some numericals. These are all unsolved numericals of the very famous book V.V. Bhandari. Let us take first numerical on design of cylinder. In this question, we have been given brake power as 3 kilowatt, speed as 800 rpm, and IMEP indicated mean effective pressure as 0.3 megapascal, mechanical efficiency as 80%, and we are supposed to find bore and length of cylinder liner. You might recall the formulas for the same. We know that eta m is given by ratio of brake power and integrated power. Since in this question we have been given brake power and IMEP, so from this equation, since eta m is also given to us, we will find IP. So IP will be PMIP LAN over 60, where A is area of cylinder, which is given by pi r 4 d square, and N is number of working strokes. Since this is a 4-stroke engine, so that will be N by 2. So we'll find IP from here and we'll put IP in this equation. So unknown left will be length of stroke and area of cylinder. Putting all the values, pressure as 0.3 megapascal, and now this equation is having two unknowns, so we reduce them into one unknown. We know that for a cylinder the ratio of length of stroke to the diameter of bore is 1.5. So assuming L by D as 1.5, length of stroke will be 1.5 times T upon 1000 in meters. So area will be pi d square by 4. Now there will be only one unknown in this equation, and that is diameter of bore. Number of working strokes is N by 2. Since N is 800, so it is 400. When we will keep all the values, this is integrated power, this is pressure, length 1.5 d upon 1000. Since it was in millimeters, so we have converted that into meter to balance the units, and area is pi d square by 4 and N is 400. So D comes out to be 116.75 mm, or we can say rounding of 118 mm. And since length of stroke was 1.5 times T, so it will be 177 mm. Now we know that we need to find length of cylinder. Length of cylinder is 15% more than the length of stroke. So length of cylinder L will be 1.15 times length of stroke, that is 203.55 mm, or you can say it is 204 mm. So our answers are, for the given question, we found D as 118 mm and length of cylinder as 204 mm. Coming to the next question. In this question, we have been given bore of cylinder as 120 mm, maximum gas pressure as 4 megapascal. Cylinder head is made of cast iron with stress as 40 megapascals. We need to find thickness of cylinder head and also number of studs, their diameter and their pitch. We know this formula for finding thickness of cylinder head, where D is diameter of bore, K is some constant which is 0.162 for cast iron, Pmax is given to us as 4 megapascal, and sigma C is permissible circumferential or tensile stress which is 40 megapascal. When we put all the values, we found TH as 15.27, say 16 mm. Now we need to calculate number of studs, their nominal diameter and their pitch. This is the relation for finding number of studs. Minimum number of studs should be 0.01 D plus 4, since D is 120 mm, so that comes out to be 5.2, and maximum number of studs should be 0.02 D plus 4, that is 6.4. So in this range we can assume studs as 6. So our studs will be 6 for this question. Now our next job will be to find diameter of studs. We know that the load acting on the studs is pi d square by 4 into Pmax, and the resisting force is Z is number of studs. This is area of one stud, and this is permissible stress for stud material. When we put all the values, we found DC from here, that is core diameter of stud 13.86 mm. We know that nominal diameter D is DC upon 0.8, so it comes out to be 17.33 mm, or say 18 mm. So we found studs as 6 and nominal diameter of stud as 18 mm. Now pitch of studs, we know this relation. It is D plus 3D. D is bore diameter 120 mm and D is dia of stud, that is 18 mm. So pitch comes out to be 174 mm. Pitch circle diameter comes out to be 174 mm. If this is pitch circle diameter, then pitch will be pi dp over z, that is number of studs, that is 91.11 mm. We need to check whether this is within the permissible limits or not. Minimum pitch, we know it is 19 root d, which is 80.61 mm, and maximum pitch is 28.5 root d, which is 120.92 mm. Since our pitch is 91.11 mm, which is within this permissible limit, so 91.11 mm is the final answer. So we have found in these two questions that were related to design of cylinders. In the first question, we found how to calculate bore of cylinder and length of cylinder, and in the second question, we found how to calculate thickness of cylinder head and number of studs, their diameter and their pitch. The analysis is very simple. So using these questions, we can solve many more questions on cylinders, and that will definitely help in making our understanding for design of cylinders in a better way. Now let us move on to few questions on design of. Let us quickly recall what we have found when we discussed design of piston. This is the diagram of a piston, cross section of a piston. We found thickness of piston head, then thickness of rib, then radial thickness of piston rings, axial thickness, top length, piston barrel at top end, thickness of piston barrel at open end, length of piston skirt, and total length of piston. We have done the analysis, detailed analysis of design of piston. Before proceeding for the questions, you all are requested to go through the presentation. Let us solve a question on piston, design of piston. In this question, we have to found what is the thickness of piston by strength consideration, then by thermal consideration, and we need to answer many questions. So if we are familiar with the design procedure, we will be in a position to answer all these questions. Let us take them one by one. We know that thickness of piston head can be found using two considerations. One is strength consideration and another is thermal consideration. So from strength considerations point of view, TH is given by D, bore diameter, P max, maximum pressure, and sigma B is permissible stress. If we keep the values that has been given to us, D as 100 mm, P max as 5 megapascal, and sigma B as 37.5 megapascal, TH comes out to be 15.81 mm. Now we'll find thickness of piston head by thermal considerations also. We know this is the relation for finding thickness of piston head by thermal considerations, where H is given by this heat absorbed by piston and BP is given by this formula that we have used while we designed cylinders. So first we need to find BP from the given diameter. Then since C, fraction of heat absorbed by piston, HCV and M, specific fuel consumption, are given to us, we can find H. Here also value of K and TC minus TE is given to us. So while putting value of H, TC minus TE and K, we can find what will be thickness of piston head by thermal considerations. While using this formula, we should be sure that we need to put brake power in kilowatt because we have multiplied this by 10 to the power 3. That means for balance of units, H should be in watts. Then only we can find thickness of piston head in millimeters. So putting all the values, H is 1551.57, 12.56, K given to us as 46.6, and TC minus TE, that is temperature at the end, at the center of piston head, and temperature at the end is 220 degrees centigrade. So when we put all the values, the thickness comes out to be 12.05 mm. Now third question is, which criteria decides the thickness of piston head? We know that we need to find the thickness using both the considerations, that is strength and thermal considerations, and the approach that gives us higher value of cylinder thickness, piston thickness of piston head, that will be considered as the criteria. So in our question, we have concluded that thickness of piston head obtained by strength consideration is more than that obtained by thermal considerations. So strength criteria will be shall decide thickness of piston head. Now we need to make decision that whether ribs are required or not. While we learned design of piston, we saw that if thickness of piston head is more than 6 mm, ribs will be required, and if it is less than 6 mm, ribs will not be required. Since for the given data thickness of piston head comes out to be 15.81 mm, which is definitely more than 6 mm. So ribs will be required. Next question we need to answer is calculate number and thickness of piston ribs. We know the empirical relation for this. We can take 4 to 6 ribs. Let us assume that we have taken 4 ribs, and thickness of rib can be 1 by 3 to 1 by 2 of thickness of piston head. So calculating this, the range comes out to be 5.27 mm to 7.9 mm. So let us assume a mid value as 7 mm. So 4 ribs will be required of 7 mm thickness. We need to take another decision whether cup is required or not. We know that cup is required when L by D is less than 1.5. In our case, length of stroke upon diameter of piston is 1.25, so cup will be required. We also need to find radius of cup. We know the empirical relation that the radius of cup should be 0.7 times diameter of bore. Our diameter is 100 mm, so radius of cup will be 70 mm. So using the concepts, the design procedure that we have laid down while we studied design of pistons, we can answer many queries and solve the design problem. Let us move on to another variant in which the focus will be on the number of rings and piston rings and their axial thickness and radial thickness. So in this question, we need to find radial thickness, radial width of piston rings, axial thickness of piston rings, gap between free ends of piston rings before assembly and after assembly, width of top end, width of ring grooves, thickness of piston barrel at top end, and thickness of piston barrel at open end. It is worth mentioning that when we discuss the design of pistons, we concluded that only few key dimensions are need to be calculated, and other dimensions we can convert in the form of the key dimensions. The same principle will use over here also. This is cross section of a piston ring where B is radial thickness and H is axial thickness, and this G is gap which we are supposed to find. So here we'll find B and we can convert H in form of B. So B is given by D, diameter of bore, PW is pressure, and sigma T is permissible stress. When we put the values, our B comes out to be 3.42 mm, or we can say 4 mm. So radial width of piston rings is 4 mm. Second question is, we need to find axial thickness of piston rings. We know that this H is in the range of 0.7 to 1 times B. So it is coming out to be in the range of 2.8 to 4 mm. Let us assume axial thickness as 3 mm. Next is gap between free ends before assembly. We saw that the gap between the piston rings before and after assembly is different. After assembly, the gap is much smaller. So the empirical formula for gap before assembly is 3.5B to 4B. Since we have already found B, so gap comes out to be 15 mm. And when the piston rings have been assembled, the gap is given by this relation. So gap comes out to be 0.3 mm. Top length, the distance from the top of piston to the first piston ring is called top length, and it is denoted by H1. We can convert this H1 in the form of TH, that is thickness of cylinder piston head. So H1 comes out to be 16 mm to 19.2 mm, assuming a value in between of 18 mm. So our H1, that is width of top length, comes out to be 18 mm. Next is width of ring grooves. This is the distance which is called as width of ring grooves and divided by H2. So H2 is in form of H, it is 0.75 H2H, where H is axial thickness we've already found. So H2 comes out to be 2.5 mm. Next is thickness of piston barrel at top end. This is the cylindrical portion which is called as piston barrel, and this is T3 at top end and T4 at the open end. So using these simple empirical relations which are given in the data book also, we can find thickness of piston barrel at top end and the open end. Let us move on to the next question. In this question, we are supposed to find the length of skirt and length of piston. We have been given various parameters. Let us see how we can use these to find length of skirt and length of piston. This is the diagram where this is called as length of this is piston skirt. We need to find its length. You can see that this skirt acts as a bearing surface which takes up thrust load. So we'll use this relation which is equal to the side thrust taken by piston equals to mu is friction coefficient into maximum pressure, maximum load coming onto the piston. So in this question we have been given that the side thrust taken by piston to the maximum pressure is given by 0.1. So mu will be 0.1 over here. PV is given to us as 0.45 megapascal. D is area dia of diameter of bore, which is 100 mm. LS is length of skirt, which we are supposed to find. Mu is 0.1. D is again 100 mm, and P max is 5 megapascal. When we put all the values, length of skirt comes out to be 87.27 mm. Now we need to find length of piston. You can see that this length of piston comprises of this width of top length, then comes this ring section, and then the length of skirt. We have already found this length of skirt. Top length width is given to us, so we need to find this length of ring section. Ring section will be number of rings into h, which is axial thickness of rings, plus n minus 1. Since there are four rings are been given to us, so the ring groove will be 4 minus 1, that is 3 into thickness of ring groove plus ls. When we put all the values, it comes out to be 124.77, say 125 mm, and empirical relation suggests that length of piston should be 1d to 1.5d. Since our d is 100 mm, so the range is 100 to 150 mm, and what we are coming up with the formula, it is 125 mm, which is in the permissible limits. So with these few questions, we tried to understand the design procedure of cylinder and piston. I'm sure that you will go through the same and you will solve more questions on design of cylinders and pistons for better understanding of the concepts that we have learned. In the subsequent presentations, we'll solve numericals on connecting rod and crankshaft also. For your patient hearing.